Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we will continue our conversation about applications of Taylor series expansions, and specifically we're going to focus on finding the errors or error bounds for our estimations. That ends up being a huge topic if you move into advanced theory in upper division mathematics or numerical analysis. This video specifically is going to be focused on Taylor's inequality. First example we have here is a function f of x equals e to the 3x squared. And what we're going to do is approximate our function f using the third Taylor polynomial expansion, or the third degree Taylor polynomial expansion, about a equals 0. Remember, if I say the third degree Taylor polynomial expansion, I really truthfully mean expand out the Taylor series until you get to a third degree polynomial. When I say centered at 0, that just means a is equal to 0. Again, a lot of instructors will call them Taylor series or Taylor series centered at 0, when in truth, they should be called Maclaurin series, but I would much prefer to call them Taylor series. So let's go ahead and write down at least the base Taylor series for e to the x. Once we have that written down, we can go ahead and trade out that x for a 3x squared because, well, that's what we're looking at here. So doing so, we get the following. And now we're going to go ahead and expand that out until we get to a third degree polynomial. And when I do this, I'm going to say this is approximately equal to, because the reality is we're only going to go out until we get to third degree. So that's going to be an approximation of this infinitely long polynomial. Now notice that when I expand this out, you can see I have three terms, but this is not the third degree Taylor polynomial. In reality, it is a fourth degree polynomial, and we don't want to go that far. So I'm going to erase that last term there. And that is often something that it seems weird to students, but that's actually the best we can do here. Remember, all the powers of our polynomial expansion are going to be even. So it should make sense that we can only get up to a square as far as a polynomial approximation. So I kind of like this example because it has that weird caveat in there. Now we're going to go ahead and use Taylor's inequality to estimate the accuracy of this, well, they say T sub 3, third degree Taylor polynomial expansion, but in reality, it's a second degree polynomial expansion. But we're going to test the accuracy of this polynomial approximation on the interval from 0 to 0.2. One thing you should note here is that we are centered at 0. And when you're doing an approximation centered at 0, you can kind of think of it this way. You have this number line, and you're approximating the value of e to the 3x squared at x equals 0. So you can gain some very nice level of precision about x equals 0 for quite some time if you have a lot of polynomial terms. In reality, we just want to know how accurate is our approximation if we consider a radius of 0.2. And we're going to visualize this in a moment, but I still want to kind of do all the mechanics by hand. Now, to remember Taylor's inequality, because it is an inequality that's pretty obscure, we use the fact that the absolute value of the nth remainder, which is what I call the error, is less than or equal to some number over n plus 1 factorial times the absolute value of x minus the center to the n plus first power. Remember, the center here is 0, so I'm going to go ahead and just erase the x minus a part and replace it with the absolute value of x, and then you have that still to the n plus first power. The other thing you need to note here is that the value of m is an upper bound for the n plus first derivative for our original function. And this is where things get a little bit wonky with Taylor's inequality, because the reality is in the real world or in applications, you're not going to know the function you're working with. And so that's really hard to say what is the n plus first derivative bounded by. But there are some times when that does creep into play and when you can actually use that. Now we're going to take our time. We're going to go ahead and let n equal, we'll start with letting n equal 3 here. But we're going to have an issue when we do this, because technically our Taylor polynomial expansion is not a third degree Taylor polynomial expansion. It's actually only a second degree Taylor polynomial expansion. We tried to get a third degree Taylor polynomial expansion, and so this would be t sub 3, but in reality, because it's only a maximum of second degree, we're going to call that t sub 2 of x. It's a second degree Taylor polynomial expansion. We can't get a third degree because, again, the powers on our expansion are all going to be even. And so we're just stuck with either getting a second degree Taylor polynomial expansion or a fourth. But because they don't want us to go beyond a third degree, we're going to have to be stuck using a second degree Taylor polynomial expansion. So when I do this, I'm actually not going to let n equal 3. I'm going to let n equal 2. And trust me, that's somewhat of a blessing, because that means that we only have to find the third derivative of our function rather than the fourth derivative. And that is, like I said, a blessing in disguise. So let's go ahead and see what the remainder or the error is for our approximation if we were to use that second degree polynomial. We know it's going to be bounded above by some number m, which we'll find in a moment, over n plus 1 factorial, n being 2, so 2 plus 1, 3 factorial. And then times the absolute value of x to the third power. Again, remember, it's supposed to be n plus 1 as the exponent. That's why we have the third power. And it's supposed to be x minus a, but our center is actually 0. So there's no need to write the x minus a, it's just x. The other thing you want to note here is that you're only really interested in the interval 0 to 0.2. So this bound, upper bound, you want to find the worst case scenario, not the best case scenario, but the worst case scenario. So if you take a look at all the x values you could plug in for x right here, the one that's going to give us the largest possible error is going to be the rightmost edge, or 0.2. So I'm going to erase that x and replace it with a 0.2. That's how you make that decision. Notice we're slowly filling in all the information we need. Seems pretty fast so far. However, now we need to find an upper bound for the third derivative of x. And this requires us, obviously, to take 3 derivatives of our function. Again, it's not likely going to be a common scenario because you usually do not have a function that you're dealing with. You have data that you're dealing with. But let's go ahead and use the fact that we're dealing with an actual written function to write down the first 3 derivatives. So I'm going to hyperlapse the video here, and I'll have you check my work at the end. You can go ahead and pause if you want or whatever, but I'm going to go through and do this. Now that I've got to this point, I'm just going to triple check my work here. And I did find an error in there, so good thing that I went through that and double checked. Now you need to find the upper bound for the third derivative on the interval from 0 to 0.2. One thing that I want to convince you of is that this third derivative, which is 36 e to the 3x squared times 6x cubed plus 3x, that is an increasing function. If you don't believe me, you can go ahead and take one more derivative, and find out that next derivative in line is positive. If you don't agree with me, well, an exponential function is never negative, so that takes care of that first factor. And the second factor is actually going to also be non-negative. Actually, it's not even going to be zero. It's going to be positive at all times. And so therefore, because this next derivative is greater than zero, we know the previous derivative, or the previous function, if you want to call it that, is increasing because its derivative is positive. Because it's increasing, you know that the worst case scenario that that third derivative is going to have is at the rightmost edge of the interval in question. We're concerned about this interval right here. Well, because the function, the third derivative, is increasing on that interval, we will go ahead and substitute in 0.2 into the third derivative to get us the maximum possible error. So let's go ahead and do that right now. Substituting in that 0.2 in the third derivative, I'll just look down here. And you can see it's going to be, we're going to have a decimal approximation in a moment, but I'll just go ahead and plug in a 0.2 for right now. That's what we get when we plug in a 0.2. I just wrote it in rational form just because I like ratios rather than decimals. And then we'll plug that into a calculator in a moment, but let's just go ahead and now say that since actually you are going to grab a calculator for this. So we'll go ahead. I'll do that off to the side right now, in fact. And I get the following, that this is approximately equal to 26.3. Now I have actually all the digits saved in the background, so I'm not going to use that approximation to compute anything. I'm just using it to display. But in the background, I have 26.30224655536, and so on and so forth. All right, let's go ahead and now use that decimal approximation to the maximum value the third derivative has to go ahead and find out what is this upper bound on our error for our approximation. Now remember, I am only using that 26.3 for display purposes. In reality, we will actually not use that 26.3. We'll use the decimal approximation that I have in my calculator. So I get that our maximal error is going to be a 0.035. Now let's go ahead and take a look at how bad our error actually is by hopping over to Desmos really quickly. And by the way, that is the last question there. Check your result by graphing the error. We're just going to graph the difference between the given function, which is e to the 3x squared, and our Taylor polynomial approximation, which was 1 plus 3x squared.
So we're over here in Desmos. I already actually typed in f of x equals e to the 3x squared. That's our base function that we're concerned with. And then I also typed in g of x, which is equal to our second degree Taylor polynomial expansion. Even though they said third degree, we were kind of forced to only do a second degree Taylor polynomial expansion. And I'm going to zoom in here. I also typed in what the error bound, our computed error bound from Taylor's inequality was, 0.035 roughly. And so I'll zoom in here because the interval that we're concerned with is from 0 to 0.02. Actually, in fact, let me go ahead and showcase that. And I meant to say 0.2, not 0.02. Let me color these slightly differently. There we go. So the interval from 0 to 0.2 is highlighted with those white bars, those white vertical bars there. Now let's go ahead and take a look at our approximating function, our second degree Taylor polynomial. And you can see that that second degree Taylor polynomial actually does look pretty good, right? There is a little bit of error off to the edge there, right? The blue curve is the actual function. The orange curve is the Taylor polynomial approximation. And if you want to showcase that the error on that interval is less than 0.035, we can go ahead and just take the difference between f and g. I'm going to turn them off, and I'm going to graph y is equal to f of x minus g of x. And this will be just the difference between these, and you can see The difference is really small. In fact, it's 0 at the center, and it starts to grow from that point forward. Look at the y values. The y values grow and grow and grow. By the time we get to this edge, the error is 0.0075, which is less than 0.035. Remember, the error bound is just an upper bound. It's not that the error is actually going to become that value. It's just that, and in the worst case scenario, the error will be that value or get close to that value. But the reality is often the errors are much less than that. And you can see that here. The difference between the two functions actually at 0.2 is less than 1/1000. Well, no, it's less than 1/100th at least. And we computed it should be at maximum 3 100ths or maybe 35 1,000ths. So that's not too bad. All right, that does it for this video. In the next video, we'll step away from Taylor's inequality and we'll showcase another way, an easier way actually, to estimate the error of a Taylor polynomial approximation as long as your Taylor polynomial is alternating. I hope to see you there.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.